Chapter 9, Part 3, when the population standard deviation is unknown. In these cases, we use the t-distribution rather than the z-distribution. Now just quickly, what do we mean when the population standard deviation is unknown? Well, specifically, we mean that we are going to be using the sample standard deviation as an estimator for the population standard deviation. What are some cases where the population standard deviation might be unknown? Well, that's actually quite common. Anytime we're interested in finding out some new information or setting up a new experiment, it's highly unlikely that we know the true population standard deviation. So let's start by thinking about our t-distribution. So the t-distribution is very similar to a z-distribution. And there is not just one t-distribution, but rather a family of t-distributions. All of the t-distributions have the same mean, which is 0, just like our normal z-distribution. However, the t-distribution has a variation of, width based on the sample size. So typically, when the sample size is larger, we'll see that the t will look more like a z-distribution. However, when the sample size is small, you'll see a much flatter t-distribution. The z and t distributions. So a large sample size will make the t-distribution be more like a z, and in fact, an infinite sample size will make the t exactly into a z-distribution. Notice here we're looking at a t-distribution with a degrees of freedom of 4. Now, degrees of freedom we have not yet discussed. We will do so in a later slide, but for now, let's just imagine that the degrees of freedom are in fact n minus 1. So the degrees of freedom, once again, are the sample size n minus 1. Okay, so in this case, degrees of freedom of 4, it's effectively a sample size of 5. And notice it is a very flat distribution. The degrees of freedom of 20 here, this red curve, this is a sample size of 21, and you'll notice this is less flat and is starting to look more and more like a z-distribution. And of course, the dotted blue. Comparing the z and t distribution when the sample size is small, right, when n is small, and using just a 95% confidence interval, what we'll see is in the case of the z distribution, we'll see that the z value is 1.96, as we've already learned in a previous section. However, that same endpoints have that middle 95% when the distribution is flatter, in this case with a sample size of 5, you'll notice that the t value that's associated with it is 2.776. Effectively, what it does is it makes your margin of error larger to account for problems with variation. So the equation for the confidence interval of the mean for unknown population standard deviations looks like this. And you'll notice that it's not very different than our z equations we've seen before. We have x bar, point estimate, plus or minus. Here we have t, and the t here is, of course, the t statistic that's associated with our desired level of confidence. And again, 95, 99, 90%, etc. Then you have s divided by the square root of n, and s, of course, is the sample standard deviation. So this, of course, becomes our standard error. And, of course, when the standard error is multiplied by the t statistic, that whole section after the plus or minus is, of course, our margin of error. So what are degrees of freedom? So degrees of freedom is the number of values in a final calculation of a statistic that is free to vary. In this chapter, we're working with a situation where we have only one unknown parameter, and therefore degrees of freedom is n minus 1. In later chapters, we might work with degrees of freedom that are n minus 2, and another set of different variations of degrees of freedom. So an easy example to think about what the degrees of freedom are. Let's consider the following. There's 5 students in a class, and the assignment requires that each student picks a unique country to research. The professor provides a sign-up sheet with a list of 5 countries to pick from. Here we have Canada, France, Chile, Japan, and Australia. The students take turns signing up. So let's start with the first student. How many choices will the first student have? Well, the first student would have 5 choices. The second student would end up with 4. The third student would have 3, right? For this guy here, he have 1, 2, 3 different choices. But by the time we get to the last student, the 5th student to choose, there is no more choice. Basically, he ends up with whatever country is left in the list. So in this case, how many students had the ability to choose? Well, 4, which is 5 minus 1, or n minus 1 degrees of freedom. The next slide will present to you how to read the t-distribution.
Okay, finding the t-value for a confidence interval using the t-table. Now you'll be pleasantly surprised, as this is actually a lot easier and faster to do than the z-table and the z-values. Okay, so let's have a look at our t-distribution here. And let's say we're looking for a confidence level of, say, 95%. And here, remember, we need to have the number of observations since this is a sample. Let's say we have 30 observations. And based on that, the degrees of freedom is equal to n minus 1, or 29. Okay, so our coordinates for our t-value are 95% confidence level, degrees of freedom 29. So let's have a look to see what that means. So again, we're only interested in this case in this specific row where it has the confidence intervals and this first column with the degrees of freedom. Of course, you can look in this distribution this side as well as the degrees of freedom continue here. For our case, we had n of 30 and therefore degrees of freedom is 29. Okay, so 29, and we go up to the top of this to look for our confidence level of 95%. And what we notice here is that 95%, and we have 29 degrees of freedom. We have T confidence level, or T statistic, or T value for the 95% confidence level is 2.045, and this effectively gets entered into our confidence interval equation. Let's say we had 16 degrees of freedom, and we were looking at a 99% confidence interval. Okay, therefore our t value would be 2.921. We'll use the level of significance one-tail and two-tail test for chapter 10.
Let's try an example. So we have a confidence interval for the mean and the example using the t-distribution. So we're looking at a tire manufacturer wishes to investigate the tread life of its tires. They draw a sample of 10 tires that have been driven 50,000 miles and reveal that the sample mean is 0.32 inches of tread that remained and a standard deviation of 0.09. Now this standard deviation is a sample standard deviation because it is entirely based on the sample of 10 that were recently driven the 50,000 miles. What we're going to do is we're going to look for a confidence interval for the population mean with 95%. So the next question we ask is, would it be reasonable for the manufacturer to conclude that after 50,000 miles, the population mean amount of tread remaining is 0.3 inches? So here we list all of the different parameters from the question. Our sample size, n, our sample mean, 0.32, and our sample standard deviation, 0.09. Now what we need here is what is the t-statistic for this, right? For a 95% confidence interval. So the t-statistic, as you learned in the previous section, is based on the confidence level, 95%, and it's based on the degrees of freedom. In this case, the degrees of freedom is, of course, n minus 1, or 9. Now notice here what we're seeing is we're seeing our distribution. So here we found that the t statistic based on the 95% confidence interval and 9 degrees of freedom is 2.262. So this goes into our margin of error equation, right? We multiply that by our sample standard deviation divided by the square root of 10, and we find the margin of error is 0.064. So based on the 95% level of confidence, we find that the mean tread remaining is between 0.32 plus or minus 0.0064, or specifically these range of observations. So what do we conclude here? We conclude that based on our sample, the manufacturer can be reasonably sure, or 95% confident, that the mean remaining tread depth is between 0.256 and 0.384. So when do we use the z versus the t? Okay, so there are a few arguments in terms of different ways of thinking about this, but for simplicity and to follow kind of the guidance of our book, what we'll stick to is this assessment. First question, is the population standard deviation known? If the answer is no, we go with a t distribution. If the answer is yes, we go with a z distribution. Finally, the last part of this chapter, selecting an appropriate sample size. So, selecting the appropriate sample size depends on 3 factors. First, the level of confidence desired by the researcher, and again, we're still sticking with our same few, 90%, 95, 99. The margin of error that the researcher will tolerate, and again, this will be based on the actual data. So this could be in dollars, it could be in feet, it could be in inches, etc. And the variation in the population being studied, or the standard deviation of the population. So what if the population standard deviation is not known? We conduct a pilot study. We can use a comparable study, or we can use a range-based approach. So when we don't know anything about the standard deviation, we can start with a small sample and figure out effectively what the variation is there and try to generalize. In cases where we're looking at quantitative data, the equation for estimating the sample size is found by using n equals z, which is our z based on the confidence interval of interest, times sigma, our population standard deviation, divided by the margin of error that we're willing to tolerate, squared. This e here, in fact, represents the margin of error that we created in our confidence interval in previous steps. So let's look at an example here. So it says a student in public administration wants to determine the mean amount members of a city council in large cities earn per month as remuneration for being a council member. The error in estimating the mean is to be less than 100 with a 95% level of confidence. The student found a report by the Department of Labor. If we go back to that previous slide, basically what we're saying here is this is using a comparable study, right? And estimating the standard deviation to be 1,000. So what is the required sample size? Well, let's check it out. We know that maximum allowable error is going to be $100. The z statistic for 95% level of confidence is 1.96, and the estimate of the standard deviation is 1,000. So we find that once we plug everything into our equation, we find that we need to have a sample size of 384.16. Now, of course, you can't have individuals, 0.16 individuals, therefore we always round these up to the next highest value. So in this case, what we find is the more precise we want our estimation to be, the larger the sample size we need. So notice, as the sample size is smaller, it says we're going to have more error. Larger sample sizes reduce the error. Here's one more example. In this case, we have a story about a consumer group and they want to estimate the mean monthly electricity charge. They want the error to be within $5 and use a 99% level of confidence. Based on similar studies, they found that the standard deviation is to be $20. How large a sample is required? So once again, we plug everything in and find that the sample should be appropriately 107. So the last component is finding a sample size for estimating a population proportion. Once again, there's three key factors. The first, the level of confidence desired, just like before. Second, the margin of error, being the researcher will tolerate, and this for proportions will effectively be in decimals or percentages, and the variation of the population being studied. This is based on actually our sample proportion. So here's our equation. N is P times 1 minus P times Z over E squared. Let's try an example. It says the American Kennel Club wanted to estimate the proportion of children that have a dog as a pet. If they wanted to estimate to be within 3%, of the population, how many children would they need to contact? We're going to be using a 95% level of confidence, and we've estimated that the sample proportion is about 30%. So let's plug it into our equation. And what do we find? Well, we find that 897 children should be asked about whether or not they have a dog as a pet. We find that more confidence means more samples. Last example, a study needs to estimate the proportion of cities that have private refuse collectors. The investigator wants the margin of error to be within 0.1 of the population proportion. The desired level of confidence is 90%, and no estimate is available for the population proportion. What is the required sample size? So we have to make an extra assessment here, or make an extra assumption. And that is, since we don't know the population proportion or sample proportion, we're going to effectively assume that it's 0.5. Not a great assumption, but this is what we do when we do not have a good estimation. So let's see what our results are. So our results are 0.5 times 1 minus 0.5 times our 1.65, which is the Z for 90%, over 0.10, our margin of error, squared, and we find that we should look at 69 cities. After the completion of these slides, please feel free to start your worksheet on confidence intervals.